Hey everyone, nice to see you again. As you can see, I'm obviously not in my kitchen at the moment. I'm actually in one of my research laboratories. Thought it might be interesting just to show a little bit of connection between some of the stuff we talk about on WiseGuy with actual research that goes on at the university. So a couple weeks ago, we were discussing this little spark generator here. And we said the way that that works is I can make a high voltage between the two wires, enough to drive a spark, several thousand volts. And the magic, we said, was really in the other end of this. So there's this piezoelectric material, and that's what we were discussing. So let me just call up a slide talking about this. So remember, this is a material that if I can compress it or I can put some force on it, it will actually generate a voltage. And that's what's happening in the end of this. There's a little piezoelectric crystal, and when I push the button, it snaps. It puts a very fast impact on the crystal, and that makes a high voltage that then allows us to make the spark. So today I want to talk about something that's very related to that. Often in physics, there are reciprocal effects. And in this case, there's the inverse piezoelectric effect. So on the left is what we've just been talking about. If I take one of these crystals and I compress it or I put a force on it, it will generate a voltage. On the other hand, if I take a voltage and put that across the same sort of crystal, then that crystal will either expand or contract. And we can use that for a number of different practical applications. So as one example, last time we talked about ultrasound, and I talked about the fact that I have these piezoelectric elements, and they will vibrate when they're hit from the ultrasound wave that is reflected off of whatever it is we're looking at, in this case, the baby here. And because they're vibrating, then they'll be generating a voltage, and we can use that to get an image. But it turns out that the ultrasonic waves themselves are generated by the piezo elements. So by putting an oscillating voltage on these, I'm able to then cause them to expand and contract, and that's how we actually generate the waves. Okay, as another example, more from my own laboratory, we're concerned with making very, very small movements. So I want to have an actuator that's able to move something by a very small amount. So the way that that works is, here's a typical example of one of these piezoelectric crystals. It's about 2 millimeters long, and if I can apply 100 volts to it, it will increase in length a small amount, about 1/10%. So it'll become about 2 microns longer. So let's just make sure we're all on the same page with these metric units. So a meter, a little bit more than a yard, is 1,000 millimeters. So a millimeter is just about that big. And 1 millimeter is 1,000 micrometers, or 1,000 microns, as we would say. And just to put that in perspective, a human hair, the diameter of a typical human hair is something like 100 microns. If I keep going down the scale, a micron is 1,000 nanometers. So a nanometer is 1 billionth of a meter, and that's also 10 angstroms. So an angstrom is just about the size of an atom, a little bit smaller than that. Okay, so what does this have to do with our piezo actuator? Well, I just said if I can put 100 volts across it, it will expand by 2 microns. That's 2,000 nanometers. But what if I only put 1 volt on? Well, in that case, then it will only expand by 1/100th of that, about 20 nanometers. And I don't have to even put a whole volt on. I could go down by another factor of 100 to only put on 10 millivolts. In that case, then the total change in the width of this will only be about 0.2 nanometers, or about 2 angstroms. So that's really at the scale of atoms. And in fact, maybe we'll talk next time about how we can use such a device to actually make an image, basically, of individual atoms. But today I want to talk about an application more from my own laboratory. Okay, so I'm just going to show us over here. So this is a device that we have in my laboratory, several of actually. And you can see it's got a bunch of these big knobs, and each of these knobs is controlling or has within it one of these piezo crystals. And that enables it to expand a very small amount. And what are they all trying to control? Well, they're all trying to control the position of this copper plate. So the copper plate has a very small optical device on it called a waveguide. You can kind of think of it like a drinking straw, but a very, very small drinking straw. And we're trying to send in light from one side through here, through the device, and then outcouple in the other direction. The trick is, though, is that this drinking straw is extremely small in diameter. It's only a couple microns. So in order to be able to effectively couple into that, we need to be able to adjust the position of this on the scale of tens of nanometers. And so that's where it's really, really helpful, really critical, in fact, to be able to have these sort of piezoelectric controls. Okay, so next time, as I say, maybe we'll talk a little bit about how we can use piezo crystals in order to actually look at individual atoms. But for now, I hope you guys have a great week, and I'll see you later. Bye-bye.